Boker Tov and good morning to all. In the previous videos, we defined what are inner product spaces. We basically started with the Pythagorean theorem, and then we wanted to ask what is an angle or a 90 degrees angle in a general vector space. This led us to the definition of a scalar product and then inner product, and then lots of interesting examples. What we want to do today is the second step, and we want to understand what is the length of a vector in a general vector space. Okay, so let's begin. So I want to start with a reminder. First, we have the Pythagorean theorem, and then we had the definition of inner product. So for an inner product, we need a vector space over the complex numbers or over the real numbers, and a function which takes two vectors and returns a scalar. And this function should satisfy three conditions. First, it is non-negative, so the inner product of a vector by itself is non-negative, and it is zero if and only if the vector itself is zero. It should be Hermitian, so if I switch the order of v and w, it is the same up to complex conjugation. And finally, it is linear in the first variable. Okay, this is what we have so far. And now what we want to understand in the Pythagorean triangle above me is the x, y, and z, right? The length of the sides. So in general, we still don't have this length, but we can always talk about vectors, right? So I can take the first vector and call it v, the second call it w, and then the third one is v plus w. And now I want to ask, what should be the definition of the length of the vector? So as usual, we go to our prototype, we go to the Euclidean standard geometry and ask what happens there, and then try to generalize it. So this is the question. What is the length of a vector in the standard Euclidean geometry? Well, by the Pythagorean theorem, this is just the square root of the sum of squares of the coordinates. This is exactly what the Pythagorean theorem tells us. Now I want to express it using only inner products, and luckily for us, the sum of squares is exactly the scalar product. So everything is just a square root of the inner product of v by itself. Okay, so now we have this new way of writing length of vectors. So let's just define in general the same expression. Right? We're going to say that the length of a vector v is the square root of the inner product of v by itself. Right? And we call this expression the norm of v. And we use like absolute value, but with two lines to emphasize that this is the size of a vector and not just the size of a number. So again, we started with the standard definition in the standard Euclidean geometry. We generalize it into a general inner product space. And now we want to understand whether all the intuition or most of the intuition and results that we have from the standard geometry still holds in the general inner product. Okay, so this is our goal. However, once you have a new definition, once you have this new notation, you must make sure that it is well defined. Now, in our case, the inner product of v by itself is always non-negative. So when we talk about the square root, we can always assume that it is the non-negative square root, and therefore this is well defined. This is a well-defined function, and we can actually use it. Okay, so now we have this new notation, new definition. What can we say about the Pythagorean theorem? Well, instead of x, y, and z, we can write the norm of v squared and the norm of w squared and the norm of v plus w squared. Right? So this is the result of the Pythagorean theorem. However, we still need the condition. We still need to show that the angle between v and w is 90 degrees. And we already know how to write it. Right? The angle is 90 degrees if and only if the inner product of v and w is 0. So this is the general Pythagorean theorem in a general inner product space. However, before I continue, I just want to mention that this new theorem is not equivalent to the original Pythagorean theorem. Actually, this one is much simpler to prove. It is almost trivial. And at least for this video, take it as an exercise. Show that this theorem is really easy to prove, and try to understand why it is not equivalent to the original theorem. Okay, we'll talk about it more in future videos, but for now, take it as an exercise. Okay, so now we have this new definition, this new notation of a norm of a vector, which is the square root of v times v. And we want to show that it has very similar properties to what we think about as the length of a vector. Okay, so the first property is that it is non-negative. It is already very interesting, right? We want the length of the vector to be non-negative. The second property talks about taking the norm of some scalars times v. So if you think about the length of a standard vector, and if I ask you, what is the length of 5 times this vector? Then you will tell me, okay, it's going to be 5 times the length of the original vector. If on the other hand, I will ask you, what is going to be the length of minus 3 times the vector? It is going to be 3 times the length of the original vector, right? If I multiply by minus, it only changes where my vector points at, but not the size. So if we expect this new definition to somehow generalize the length of a vector, then we expect that the norm of alpha times v is going to be the norm of v times the absolute value of alpha. Okay, so let's show that this is actually true. So first of all, by definition, the norm of alpha v is the square root of the inner product of alpha v by alpha v. Then we use the linearity in the first variable to take one of the alpha outside of the inner product. Then the linearity or semi-linearity in the second variable, we can take outside the second alpha, but with complex conjugation. Then we have alpha times alpha conjugate, which is just the absolute value of alpha squared, which we can take outside of the square root. And finally, the square root of v times v is just the norm of v. Right? So these are basically almost directly from the definition. We get that the norm of alpha v is the absolute value of alpha times v. Okay, so now we have these two very natural properties, which is what we expect from any type of generalization of a length of a vector. And in order to understand the third property, I first need to get rid of the right-angled triangle, and let's look on a general triangle instead. And again, I can name one of the sides by v, and the second by w, and the third one is v plus w. And in order to understand this new property, let's say that I want to go from point A to point B. Then one of the most basic intuitions that we have in geometry, that I think we use on a daily basis almost all the time, is that if I want to go from point A to point B, I can first go by v and then by w, but we know that the fastest route is going by the straight line, meaning going by v plus w. Or more formally, this is the triangle inequality, which says that the length of v plus w is less or equal than the length of v plus the length of w. Right? The fastest route is the straight line. So this is the triangle inequality. This is what we expect from general length of vectors. And this is a property that is also true for general norms. So again, this is a theorem, the triangle inequality. The norm of v plus w is going to be at most the norm of v plus the norm of w. Now, the proof of this theorem, at least in my opinion, is very interesting, has a lot of geometric intuition, and of course it should have because it is a proof of the triangle inequality. However, it is a little bit long, so I will do it in the next video. And what I want to do in this video is talk more generally about norms and try to understand what happens. Okay, so in our discussion so far, we started with an inner product. We defined what is the norm of the vector using inner product, then gave these three properties of this new function and said that these are very important and useful properties for a function to be a generalization of a length of a vector. So this is very similar to what we did in the definition of inner product. We looked on one function which is very important and very useful, the length of a vector. We asked, what are the interesting and important properties? And now that we have them, these three properties, we can say, let's define a new structure, a function which satisfies these properties, and ask what can we say there. Not just talk about length of vectors, but talk about structures which satisfy these properties. Okay, so let's really have a new definition. We call it the norm. So for defining the norm, we need a vector space again over the real numbers or the complex numbers. And the norm is going to be a function from the vector space into R, which again, we think about as the generalization of a length of a vector. And it needs to satisfy the three conditions from before. It should be non-negative. So for every vector, the norm should be non-negative. And it should be zero if and only if the vector itself is zero. It should be absolute homogeneous. So the norm of alpha times v is the absolute value of alpha times the norm of v. Or you can think about it as sort of multiplicatively, right? So the norm of alpha v is the norm of alpha times the norm of v. And finally, it should satisfy the triangle inequality. Norm of v plus w is at most the norm of v plus the norm of w. Okay, so this is the definition in general. And basically what we said before is that we have this theorem, whenever you start with an inner product over some vector space, then the function that we define as the square root of the inner product of V by itself is going to be a norm, right? It's going to satisfy these three conditions. Now, in the previous videos, we have seen that there are many examples of inner products, and therefore there are many examples of norms induced by these inner products. However, not all norms are like that, and there are some very important norms which are not like that, and I want to show you a few examples. So when we talk about examples of norms, then first of all, we need to take the obvious one. So again, the induced norms is type of norms. The second example is more like a family of examples on vectors on the complex numbers. You can also do it on the real numbers. So the first norm in this family is again the induced norm, which is usually called the Euclidean norm or the L2 norm, which is just the square root of the sum of squares. Okay, so this is the first example. The second example is called the infinity norm or the L infinity, and it is just the maximum value of the maximum of the absolute value of the coordinates. Okay, so we have these two norms, and we differentiate between them by adding the subscript of 2 and infinity. And the second norm, this L infinity norm, is not induced by an inner product. Right? The L2 norm is of course induced, the second norm is not induced. Now, both of these norms are very important, very useful, appear in many, many places. And if you ask me which one of them is better, then, well, if you look at the L infinity norm, then in a sense it is much simpler, right? I don't have the squares, I don't have the square root, I don't have the summation, I only have the absolute value and the maximum over it. So it is simpler in this sense. On the other hand, the L2 norm, while more complicated, has all the structure of inner product behind it. So I can use many more tools in order to understand it. Okay, so each one of them has pros and cons. However, if you already learn a little bit of calculus and calculus in several variables, then maybe you talked about when does a sequence of vectors converge to zero, and your original definition was, well, if the sum of squares of the coordinates goes to zero. Or in other words, the L2 norm goes to zero. And then you said at some point, you know what? This is a little bit difficult to work with. And you showed that this is equivalent of saying that the maximum value, the maximum in absolute value goes to zero. So basically, if you know a little bit of calculus in several variables, you have seen that the L2 norm and the L infinity norm are in a sense equivalent. They are distinct by equivalent. Right? So we want to work with the L2 norm because of all the nice inner product structure behind it, but it is a little bit difficult. And on the other hand, we might want to work with the L infinity norm because it is much simpler. And this little claim shows that you can move from one to the other and not lose too much. Okay. So these are two norms. The third one in this family is called the L1 norm, and it is the sum of the absolute value of Vi. This is again very important, very useful, a little bit less I think from the L infinity norm, but again you will find it in many places. And finally, these three types of norms is actually part of a very large family called the LP norm, where P goes from 1 to infinity. And the definition is you sum from 1 to n the absolute value of Vi to the power of P, and then you take the root of 1 over P of everything. Right? So if you plug in P equals 1, you get the L1 norm. If you plug in P equals 2, you get the L2 norm. You cannot plug in P equals infinity, but if you take P to infinity and the limit, you get the L infinity norm. Okay, so we have already infinitely many norms on C today. And actually, if you look on this family and you take the P equals 2 outside, then all of these norms are not induced by by any sort of inner product. Right? They are all distinct and not induced by an inner product. Okay, so now we have a new family of examples of norms on the more discrete vector space C to the n. And in many cases, when we have anything to do with addition, we have something similar with integration, and this is one of these cases. So we can talk about family of norms on continuous functions on 0, 1, and we denote them by LP with capital L, and they are defined similarly. right? The integration between 0 and 1 of fx in absolute value to the power of p and everything to the power of 1 over p. And just like in the addition part, the L1, L2, and L infinity norms are very, very important. And you might even came across them several times before, but not call them norms. For example, the L infinity norm is just the maximum value of fx on the segment 0, 1. By the way, we're talking about continuous functions, so I can actually take maximum. If we're talking about more general set of functions, I need supernorm. In any case, we have this L infinity norm. And if you're already familiar with the concept of uniform convergence that you learned about in calculus, then actually uniform convergence is basically convergence in the L infinity norm. So what do I mean by that? To say that a sequence fi converges uniformly to f means that not only fix converges to f of x for every x, but you do it simultaneously. And if you write it formally, this just means that if I look at fi minus f and I take the L infinity norm, it goes to 0. So uniform convergence is exactly convergence in the L infinity norm. Okay, so you see that it appears there. Now, if you already studied this uniform convergence, then take it as an exercise, go back to your notes, and see that almost every time that you do anything to do with this uniform convergence, you basically use the properties of a norm, and in particular, the triangle inequality. Okay, so today we talked about norms and saw how they are in a sense generalizations of a length of a vector. What we'll do next time is prove what we still need to do and show that the triangle inequality is always true for the induced norm of an inner product. Okay, I'll see you next time.